Hi, so in this video, I'm going to be showing how to make a phase diagram given the molar free energies of mixing for two different phases in a binary system. So in this video, this will be the orange phase, and this will be the blue phase. So firstly, I wanted to manipulate the solution models to see which temperatures would be interesting for the phase diagram. So at 0 degrees Kelvin, we start out in the blue phase, and we know there's going to be a sphenoidal region. Then, as the temperature increases, we know we're going to get two phase regions. And finally, the orange phase descends, and we know that we're going to have all orange phase at all compositions. We know we get two phase regions because of the common tangent construction, which says if there exists a common tangent, the system will lie on that common tangent to reduce Gibbs free energy. So the interesting part of this problem is calculating the common tangent constructions. And we can do this given some code inspired by Professor Carter's code, which takes in a function, says, okay, I'm going to find 2 points on this function where the derivatives are equal and the intercepts of lines tangent to the point on this curve are equal. The y-intercepts. And we know that if the derivative is equal and the y-intercept is equal, they lie on the same line, and this must be a common tangent composition. And we have to use the find root function because this is a computationally difficult problem, and find root takes in guesses, which makes it easier for it to solve the equations. So what I wanted to do was create a piecewise function that would just display the curves with the lowest Gibbs free energy. So to find common tangent compositions, we don't care about this part of the curve. What we care about is this part of the curve. So I found where the curves intersected. Then I found which solution model started out with the lower Gibbs free energy. And then I just created a piecewise function by flipping which solution model to use at every time that the solution models intersected. So starting out at 0.33 degrees Kelvin, we would expect for this piecewise min function to give back a curve that looks like the blue curve, then the orange curve, and then the blue curve. And that's what we get. So we know that this function is working. So we can use the piecewise function and the gas compositions function to generate the common tangent compositions at every temperature. So we use a table to do this trick where we assign the compositions found at one temperature to this dummy variable called last guesses. Then we feed last guesses back into the gas compositions function for the next temperature. And this gives guesses that are close to the real composition. This only works if there are no jumps in where the common tangent compositions are. And I found that there were 2 jumps. So to make this work, I had to make the tie lines in 3 different tables and then join them together in one table. Finally, I used some of Professor Carter's code, which generates a tie line between the 2 points of every tie line in this tie lines list, and then plots them. So this is the phase diagram that we get. We see there's a blue region here and here with the sphenoidal that we expected. And then there's the orange phase up here with the 2 phase regions of orange and blue here. Finally, we can see the common tangent that we calculated, starting at 0, blue with itself, and the red line changes as we increase temperature up until 1.35 degrees Kelvin. I got an error past 1.35 degrees Kelvin, and I think this has to do with the computational difficulty of the find root for this system. All right, thank you, that's it.